whole topic. Don't be concerned if you start getting a little overwhelmed, but do slow me down if something completely makes no sense to you at all. I'm going to try and support the key ideas to do with aqueous systems with some very simple, very quick demonstrations that use copper carbonate as our context for this. So here we go. The first thing I'm going to remind you about is something that you learnt in previous years to do with solubility. And there was a set of rules that you were given in level 1 and in some of your assessments in level 2, particularly the ions in solution one, where, for example, you found out that all carbonates were insoluble except for potassium and sodium carbonate, for example. You found out that things like barium sulfate were insoluble. You found out these rules about things that created a precipitate if their ions were present. So one of them, and the one I'm going to focus on, is this. Now, we kind of lied to you. They're not completely insoluble. Because they're ions, they have to be partially soluble at least, because they can be surrounded by water molecules and therefore removed from the crystal or from the powder. So they are at least slightly soluble. So really what we say now is not that they're insoluble, but that they are sparingly soluble, which means only a little bit dissolves. So now we say that the things that we did call insoluble are now sparingly soluble. Remember that in chemistry, we're really worried about being able to show things with a chemical equation to show what the heck is happening. So what I'm going to do is put a little bit of the powder, copper carbonate, into some water in a test tube and describe what we see happen. And it's not going to be exciting, but we do need to be able to use a chemical reaction to show it, or a chemical equation I should say, to show it. So I've got a small amount of this green powder and I put it in, and I don't really see much happen at all. It just sinks to the bottom, and if I leave it long enough it will settle out, and there'll probably be no observable colour to this solution. Okay, so even as I put it close, that's not turning green, which is why I called it insoluble. However, if I could zoom in enough, I would find that the concentration of carbonate ions has increased, and so has the copper 2+ ion concentration, just a little. And if because I've done this mathematically, I actually know that it's gone up by about 1.2 times 10 to the negative 5 moles per litre. Okay? And that's because I know the solubility of this, even though we called it insoluble in previous years. Because I'm not observing any more change, what do we call this type of system, if we can remember year 12? No observable change, but I actually have to believe that there is something happening, dissolving and precipitating occurring all at the same time.
Equilibrium?
Well done. It's what we call a dynamic equilibrium, where we have a forward and a reverse reaction occurring at the same rate, which amounts to no observable change. So what I put in there was copper carbonate. It was a solid. Now, before I started this video, I said to you, anything that is not dissolved in water, we don't care about mathematically. But we sure as heck have to care about it because it's sitting there at the bottom. But mathematically, we're not going to care about it. Okay, it's not going to be important, actually. There's nothing else that it's reacting with, except for the water. So I don't need to put plus water here. It is implied by what I put on the other side of the equilibrium arrow, that it has made some copper ions and some carbonate ions. I'm asking you to believe me that they're in the factor of 1 particle in every 10,000 roughly. That's not quite right, 1 in every 100,000 roughly. Not many particles are going to be these ions, but they're there, and I'm asking you to believe me at the moment. Later on in the unit you might do some experiments to actually prove this sort of thing, but we're only doing an overview. Now, because it's an equilibrium, this is what we call an equilibrium equation. Okay, so just reminding us that this is called an equation. What can you write for any equilibrium? And again, you met them last year. There was a set of rules, well, a little A plus B, B goes to C, C plus D, D. What do we write? An equilibrium constant. It's what we call an expression. an equilibrium expression. We called them Kc last year for a constant, basically, Kc. This one is a special one, and I've put it above. It's Ks, because it's about something being dissolved. It's about solubility. So that's going to be our first topic. It's all about the link and relationship between Ks and how soluble or insoluble something is. But we have to know how to write these, because the rules we were given last year are a little bit too simple. For this, because it's going to be a number, so there's some maths involved, I only care about the things dissolved in water. Because it's got maths involved, I only care about the aqueous stuff, which means states of matter are very, very important in this topic. So Ks will equal the concentration of copper ions. Now I'm going to take the AQ out, because I'm writing it only because it's aqueous, times the concentration of carbonate ions. Now, if one of those had a number in front of it, what would I do to this? So if, say, it was 2 coppers but 1 carbonate, what would I do? Struggling to remember? Rather than writing a 2 in front, it becomes to the power of. Okay, so just reminding us that our little Kc rule, as it were, hope that fits on the video. So we had that little Kc rule. This will be true for everything we do. Now I can see quite clearly that not much of this is dissolved. So what I'm going to do is filter it, because I need the solution. I don't need this. The solution that I've got sitting above this, by the way, has a special name. It's called a saturated solution. I cannot dissolve any more copper ions in there or carbonate ions, because if I try to, it will actually push the equilibrium in the reverse direction, creating more solid. And because my maths is only about things that are dissolved, then I don't care about them, because they're going to be precipitated out. But I need the solution for what I'm going to do next. And it won't take long to filter, because I've actually got most of the solid stuck in the bottom. So we'll just let that drip its way through. And while I do, I'm going to go to the next bit that we're going to cover. So, Ks and solubility is the first thing you're going to be looking at. Oh, I did say that I could tell you how much was there, by the way. And the reason is that I know the Ks value for this. Just give me a bit of paper, because I'll forget otherwise. At the current temperature, which is just above 20 degrees Celsius, I found that the Ks value is 1.4 times 10 to the negative 10. So that number is 1.4 times 10 to the negative 10. Now, the fact that I've come from the same thing, so the carbonate hasn't come from somewhere else and the copper hasn't come from somewhere else, I know that they're in the same concentration, don't I? So therefore, the concentration of each of those ions would be the square root of, so it doesn't matter which one I do, it would be the square root of the Ks, which is this. And I said to you it was going to be something times 10 to the negative 5. I think that's pretty obvious. We have a power to the negative 10 being squared. Okay, and that will be in moles per litre. So that's an important link that we're going to explore later in this lesson, actually. Right, this is done enough for me. I now have got my saturated solution. It looks very, very colourless to me, so hopefully when you look at the video you'll see that I'm not lying to you. And I'm going to put some universal indicator solution in it. And it does nothing, it stays at green. If I had something much, much more precise than just universal indicator, I would find that the pH might have raised just a little bit. Why would the pH be just a little bit higher than 7 with a carbonate? Why would that be? The hints are in the things I said we're going to go through here. Maybe the little subscripts next to the K values might give you some clues. A, B, and W, what could they stand for?
Is carbonate a base?
It's a base, good. So the next thing is we've got pH, Ka, Kb, and Kw. Okay, now I know this is still at 7 because our universal testing solution isn't precise enough to tell us that it's ever so slightly above it. But the carbonate ions in there have actually raised the pH ever so slightly, if we're precise enough. How could I show that mathematically? How could I show that with an equation? Which of these ions in solution has affected the pH, albeit not enough for us to measure with UTS? Carbonate. So I can write carbonate. It's aqueous, so I do care. And what does the carbonate react with when it's in a solution? Very good, water, because it's an aqueous solution. So this time we do use water. Notice it's a liquid. Okay, this is important for doing the K value at the moment. It's a weak base, and we know that because it hardly changed the pH. Okay, it's a weak base. What do bases always make? Which is why they do have an effect on indicators. Which ion do they always make, which is why they have an effect on indicators? OH, good. So they will make hydroxides, which are dissolved in water. Just going to put a little bit of blue underneath it, just to give us that hint. Okay? That's the ion that makes litmus turn blue. Okay? That's the ion that affects it. And what's going to be left over there? This is a base, so what does it make? What do we call the thing that a base makes? Conjugate acid, very good. So over here I'll write the word conjugate acid. Hopefully this is bringing lots of stuff from last year back. And what's the formula for its conjugate acid? We're getting there. I heard H is mentioned, which is good. HCO3. By the way, HCO3 is a base, but it's called a conjugate acid there. It's all semantics, it's just what they're called, okay? When a base acts as a base, it gains a proton, which is what it's done. It makes a thing we call the conjugate acid, even if it is alkaline. That's got a pH above 7, okay? But I want to show you that it actually can act as an acid. Okay, I want to show you that it can. It's actually what we call amphiprotic. It can act as an acid or a base. But if it was acting as an acid, okay, I want to prove that it can act as an acid. What do acids do? Bronsted-Lowry definition we're after here. What do they do? If this gained a proton to be a base, what do you think an acid does? Loses one. Cool. And I've put the equilibrium arrows in there already. Okay, so let's lose it. CO3 2 minus. Oh, okay, that was pretty familiar. So what do we think we call that if it's what the acid got turned back into?
Conjugate base.
Conjugate base. Cool. And what's the other ion being formed? And this is the thing that makes indicators change colour.
Hydrogen.
Not just hydrogen.
H plus.
Bit more.
Hydrogen.
Hydronium. Very good. We need to be just a little bit more specific now. So we've got hydroniums. I put a little bit of red squiggly line under that one, because that's our thing that makes an acid, makes an indicator like litmus turn red or yellow or orange or whatever colour it is for that. Okay, now put all these things in because we have to remember all our maths when we get to this topic in about a week and a half's time about calculating pH from our hydronium ion concentration. So that pH is the negative log of the hydronium. We need to know the relationship between pH, Kw and hydroxide ions. All that stuff becomes important again. But there's two new things in here, Ka and Kb. Which line, 1 or 2, do you think we would write a Ka for? 1 or 2? Second one, because it is an acid. This is, without meaning to be patronising, this is the acid dissociation constant. So you can only do it for an acid. Using our little rules up here, and remembering we only care about things dissolved in water. That water is a liquid, okay? Its concentration stays the same. So it'll be the same on the top and the same on the bottom, because its concentration will be the same there as it is there. So what do you get whenever you have the same number on the top in an equation and on the bottom if it's a division? What? Cancels out, so it becomes 1, doesn't it? So we don't include it. But we do need to put these in. Again, I've got rid of the AQ because I've used the AQ to decide what I am going to put in the equation and what I'm not. So therefore, this one must have a KB. And they're not dissimilar, actually. What would be on the top? The concentration of which two species? OH, yep. Anything else? Cool. So that's showing me we still have a bit of a recollection of how to apply this. And on the bottom will be our carbonate ion. Now there is a relationship between these two, which I'm not going to go into now. But if you multiply that by that, you get 10 to the power of negative 14. What's that? What's 10 to the negative 14? Do you remember that from last year? It's to do with pH. We use it when we know that, say if we've got a strong base, we know the hydroxide concentration. We use it to find our hydronium concentration. It's called our KW, which is the last thing that I put up here. If I multiply these two together, you'll actually see that things start cancelling each other out. And it just ends up being hydroxide times hydronium, which is our water dissociation constant that we learnt last year. The only other thing in this topic, and it's not going to work, but I'm going to show it to you anyway, is in here I've got some carbonate ions. If I was to add hydrogen carbonate ions as well, and I'm only going to add a couple of drops because I don't want to mess with it too much, then I create a system called a buffer. And if I was to add an acid or a base to this, its pH stays the same because it has both the base and its conjugate acid present in similar concentrations, which allows it to absorb hydronium ions or absorb hydroxide ions and keep the pH the same. That's the last thing we're going to learn about because it's probably the hardest bit in the topic. So, do a quick rewind. We learnt about equilibrium last year. We can apply that to things dissolving because the things we used to call insoluble we now know dissolve at least a little bit, which means we can write an equilibrium equation and therefore write an equilibrium expression called Ks, or solubility product. From that, and we're going to get to that later, we'll learn about how to use that value to find the solubility in moles per litre and grams per litre of something. Also, when some things dissolve, they can be acidic or alkaline in nature, so acids or bases. And we need to have an understanding of their pH by using things called Ka, Kb, and Kw. And that helps us to work out their hydronium ion concentration and therefore justify or calculate their pH. If I then know about a weak base and its conjugate acid, or a weak acid and its conjugate base, and I have those in a solution in very similar concentrations, then I create a solution called a buffer, and buffers control the pH of themselves very, very well. And one of the best examples we could talk about would be some biochemistry about your blood, where you have got an equilibrium in your blood that uses the dissolved carbon dioxide and the hydrogen carbonate ion dissolved in your blood to make sure your pH of your blood doesn't change so that it actually can carry oxygen and carbon dioxide without those enzymes denaturing, so therefore you dying. So that is the whole topic in a nutshell. We are also going to look at titrations as well. That makes everyone groan. But in particular looking at the shapes and justifying the parts of titration curves. So don't worry, if you don't want it to be experiment heavy, it doesn't have